Okay, in this video we're going to talk about Unit 2 Objective 10++, which is polar derivatives. Um, Hopefully you watched the previous video on the website just showing you what polar functions are, how they're graphed. Much like parametric functions, you're not going to be asked to graph them, but later on when we find areas under curves, you're going to need to be able to recognize what the graph would look like. But for now, we're just going to be working with the derivatives. So you are going to have a function written in terms of r and theta for your polar functions. So r is going to be in terms of theta. R is going to stand for the radius, and theta is just the angle of your function. So your independent variable is going to be your theta. In order to differentiate polar coordinates or polar functions, we're going to need to turn these things into a parametric function, x in terms of theta and y in terms of theta. So the first thing that we're going to want to do on our polar derivatives is we're going to need to say x is equal to r cosine of theta, where r is the function that you're given. Then y is going to be equal to r sine of theta. The reason we want to do this is because derivatives are defined dy over dx, and in our original function all we're going to have is r's and thetas. So we need to introduce an x and a y, that way we can get dy over dx. Now, we've defined it parametrically now. We have it two functions, x and y, in terms of our variable theta, which means if we take the derivative of those two things, we're going to get dy d theta, and we are going to get dx d theta. And much like our other parametrically defined functions, if we're going to end up at dy dx, we need to divide dy d theta by dx d theta in order to get our dy dx. So it's very similar to what we did with parametric functions, except we actually have to take a step to go from what they give us to our parametrically defined functions. So let's take a look at an example. We'll just do an easy one. We'll say r is equal to sine of theta. So we need to find the derivative of this function. So again, we're thinking we need dy dx. So we don't have any y's, we don't have any x's, so we need to fix that problem. So we need to rewrite r sine of theta in terms of x and y. So you'll recall x is equal to r cosine theta, and y is equal to r sine of theta. Well, all we have to do first is a quick substitution. Sine of theta is r, so we want to substitute that into our parameters first. So x is going to be rewritten as sine of theta times cosine of theta, and y is going to be written as sine of theta times sine of theta, which is just sine squared of theta. So if we want dy dx, we need to take the derivative of the x in terms of theta, we need to take the derivative of y in terms of theta. So dx d theta would be, well, we have product rule. So the derivative of the first is cosine times the second, which is cosine, plus the first stays the same, so sine, and then times the derivative of the second, so negative sine. Let's get the eraser. Times negative sine of theta, which we can simplify into cosine squared theta minus sine squared theta. So that's our dx d theta. Now we need to think about dy d theta. So again, we're going to have not product rule this time, but chain rule. So we have that squared, so that's our first layer. So 2, keep the inside the same, sine of theta. Then multiply by the derivative of sine, which will be our cosine of theta. So we have dx and dy, so if we want dy dx, we simply just have to divide our y derivative, so 2 sine theta cosine theta, and divide that by our x derivative, so cosine squared theta minus sine squared theta. Now from here they can ask things like, where is your horizontal or vertical tangent lines? And again, all we have to do is set either the numerator or denominator equal to 0, depending on which one they want. So numerator would be our horizontal asymptote, denominator would be our vertical asymptote, or vertical tangent line, sorry. So that'll do it for this video. We'll see you in the next one.